Hello, everyone, and welcome to Coffee with Caleffi. Today, we're going to be talking about electronic mixing valves, the technology behind it, the applications, planning, installation, and operation with two of our internal speakers, Cody, Mack, and Dan Firkus, are going to be taking us through the slides. So I'll go through a couple of the intro slides, and we'll turn it over to those guys to walk through the content. So if you are having any issues with the audio, usually logging out and logging back in fixes it. If not, there's the tech support line for GoToWebinar. And some of the questions we get quite a bit as well. Can I get a copy of the presentation after the webinar? Hit yes to the post-webinar survey to get a copy. And then we'll also archive all of this on YouTube. So you can see about 12 years of Coffee with Caleffis on our YouTube playlist for North America. Certificate of attendance. So we will send this to you as well. If you want something, if you can self-report in your jurisdiction, we'll send you something that has the title and the amount of hours and everything like that. So one of the things that we're very proud of that's on the topic today is that the Legio Mix valve, in combination with the thermosetters and the sink mixers, we won one of 3 finalists in this year's AHR Expo in the sustainability category. So one of the cool things about this product is the reduced water waste, the reduced energy usage, and then even the potential for Legionella disinfection. That was all kind of wrapped into our submission, and we were one of 3 to take home that prize this year. So for the most recent version of Hydronics, if you signed up to get these in the mail, you would have received this in the last week or so. Hydronics 31 is on pressure reducing valves. It's also available on the website as a PDF or as more of an interactive guide through this same material at hydronics.caleffi.com. Sometimes we have video and additional links and things like that, so it's a little bit more information than just the PDF if that's what you're looking for. And then next month, I'm going to be back doing the presentation with Brent Cunningham from Grundfos. So we're going to talk about a hydronics topic with pumping, air and dirt separation, and we'll kind of go back and forth and talk a little bit about the future of pumping and ECM technology as well. That's a continuation of an in-person series that we've been doing with Grundfos called The Perfect Loop. So that'll be about a month from today. And the topic of the day with Cody, Mack, and Dan Firkus. I'll have those guys jump back in and I'll walk you through electronic mixing valves. So off to you guys. Thanks.
Perfect. Thanks, Max.
Right.
Appreciate it.
Thanks, Max.
All righty. Well, let's go ahead and get started into electronic mixing technology for your domestic hot water systems. And thanks everybody for joining us today. Before we get too far into things, just want to mention that if you have any questions, do not hesitate to type them into the questions pane. If we don't answer your questions during today's webinar, we'll definitely get back to you at a later time, probably early next week, but definitely check that out. So today, you probably noticed the topics here. I hope you can appreciate my healthy sense of sarcasm. It's highly developed from all my years in the field. Dan's got a pretty good one too. But we're going to talk about electronic mixing for domestic hot water, and we're going to kind of compare it to thermostatic as well. We're going to talk about planning, especially as engineers. Obviously, you guys are going to be looking into switching over to electronic mixing for domestic hot water and some things that you might want to look out for. We're going to talk about piping as well and how to design and get these systems drawn out to where they're going to work properly. We're also going to talk about just kind of the elephant in the room. Obviously, with electronic mixing valves, you're going to have electricity involved, programming and operation and all this other fun stuff. And then we're going to talk about troubleshooting and maintenance. We want to make sure that for the life of the building, for the life of the mixing valve, that it's going to be able to work properly and everything like that. And to be honest with you, a number of these things that we're going to talk about, they aren't necessarily 100% specific to electronic mixing valves, but it's never a bad time to cover your bases, especially again, if you're making changes to your designs or to your specs. So that way you're going to make sure that everything's going to go as well as you hope it does. So we're going to jump into this guy. First, we're going to talk about kind of that whole idea behind electronic versus thermostatic. And we're going to talk about the applications a little bit, and we kind of want to plant the seed here, when to use them, when not to use them. We're not going to answer all these questions right here on this slide, but we're going to just basically plant this seed here for you guys to make sure that you're thinking about this as we go through the rest of the slides. I do want to say too that there's going to be a number of places where we talk specifically to our Legio Mix, which is our electronic mixing valve for domestic hot water applications. So we're going to talk about some specific features that could be a huge benefit to you and your customers. So definitely check that out there too. But we're going to talk about the different types of buildings that you might have, whether it be multifamily, hotels, hospitals, healthcare facilities, just in general. You know, why you might want to work with an electronic mixing valve in those applications versus thermostatic. The idea behind thermal disinfection as well. If you're using high temperature water to basically help manage Legionella bacteria in your domestic hot water systems, that's going to be a great one to talk about for thermostatic versus electronic. And then harsh water conditions. Dan, you travel quite a bit too. Does anybody anywhere you go tell you that they have great water?
Not that I hear.
No,
Everyone's subject to water quality.
Yep. So it's always a constant battle for designers, for building maintenance guys, for contractors. The fact that you've got to deal with whatever you've got coming in from the street or the well or whatever you're working with. Everywhere I seem to go, everybody has a pretty good agreement on the fact that everybody has terrible water. And then also, if you're going to be replacing a mixing valve, or if you're just going in from a brand new spec point of view, if you're replacing a standard thermostatic mixing valve, maybe you might be replacing a high-low mixing valve as well. And then obviously, again, the electrical portion of an electronic mixing valve and how that might play into to the idea of whether or not you use thermostatic or electronic. So we wanted to talk about all these different things and kind of plant the seed here as we go forward. Okay, so the first one, we've got a big chunk of our literature here, and this might look like a bit of an eye chart, but I think we've got some of the best literature in the industry. The fact that we've got this here is a snippet right from our technical brochure. Like I said, it might be a bit of an eye chart, but it's a great tool to help you figure out what size mixing valve that you're going to be using for your application. This is a great tool, but there's just one little piece of information that you're probably going to need before you really get started using this tool. Dan, what's that piece of information?
That's going to be your design flow rates for your project. That's
your design flow rate. It's literally the very first thing that we call out in our valve sizing and selection to obtain the maximum GPM demand of your domestic hot water for your project. Okay, this is one of those things I've run into it quite frequently. Especially on the replacement side, where maybe you don't necessarily know what your flow rate is, but on a new construction building, definitely you should know what that is, and it should be called out as a design flow rate for your domestic hot water applications, as well as a design pressure drop as well. And obviously, if that's missing from the equation, it's going to cause a lot of concern and potential for errors, and it's something that we need to address. So we want to get your engagement here, and Dan, I don't know if you can keep an eye on that questions pane. So within the questions pane, we want to know how you guys are calculating your peak demand, whether it be for the whole potable distribution system or just for the domestic hot water side. We're curious how you guys are going about doing it, because obviously that's a pretty critical number to make sure that you're sizing all of your piping correctly, your mixing valves, pressure reducing valves, anything and everything in between, to make sure that everything's doing exactly what it's supposed to. So are you seeing anything in there, Dan?
No, I'm not seeing a whole lot popping up. I think it's important to remember that peak demand isn't total demand or total GPM load.
For sure. And we talked, Dan and I talked about this before, the idea that your peak demand, it's not going to correlate to however many fixtures you've got in the building. The only time that might apply is if, as Dan and I were talking about it, is a football stadium at halftime. That is one place where you can pretty much guarantee that every single fixture in the building is probably being used. But with that in mind, most of your buildings, you're going to have a lot more fixtures than fixtures being used. So calculating that probability is what you really need to be focused on to make sure that you're getting the proper flow design for your particular system. So with that in mind, you might be running into people Hunter's curves, or people using some type of code required planning for that as far as their sizing is concerned. But what we wanted to talk about here a little bit was some of the more interesting ways of going about it. The first of which is going to be what's referred to as the Hunter's curve. So if you're coming into this and you're sizing these mixing valves, you need to figure out that peak flow design or that design flow rate. You might have heard, or you might even be using still, the Hunter's curve. And the whole idea behind this is that you're putting a weighted value to each fixture in the building, and you're counting up all of those fixtures in the building to come up with a total number of fixture units. Now, once you take those fixture units and you count them all up and everything, you're going to have multiple curves across this guy right down here at the bottom. And these curves are going to be different applications. And so from there, the first curve here, like, let's just say you count up 225 fixture units. You come up to this first curve, which is an office building. 225 fixture units means 25 gallons per minute. But then if you take that up there and you go to, say, a restaurant, 225 fixture units comes out to about 90 gallons plus, or 95 gallons per minute. Big difference, huh? So it's definitely something that you need to address. Now, I guess one of the biggest problems that we run into with Hunter's curve is the fact that it's based on data from the 40s. Dan, have things changed since the 40s?
Yeah, they've changed quite a bit. And I know that's something we were discussing earlier. You look at flow rates of fixtures today compared to the 40s, and it could be half of what you saw before. So,
or less.
Or less, exactly. So you need to take that into account when you're using the Hunter's curve and coming up with your design flow rates.
Yeah, and sometimes you guys are definitely limited as designers and engineers to where you have to design it a specific way or have to calculate it a specific way. But in all reality, the Hunter's curve, I think, is a great place to start, but it might not be the place where you want to end. And we wanted to touch base really quick on another tool. If you haven't heard about it, this is a tool from the International Association of Plumbing and Mechanical Officials. They call it the Water Demand Calculator, and I think this is a really awesome tool. It's completely free, okay? From there, you can download it as a spreadsheet right from their website, from that link that's noted right there. You can also get it, I believe, as an app on your phone. I haven't tried that out yet, but what's cool about this guy is that you enter in your fixtures, you enter in your fixture flow rate for each one, and it comes up with a peak demand flow. Now, obviously, if you're going to use this for domestic hot water applications, you're going to leave out things like toilets that don't use hot water. And from there, you're going to get a number that's typically much, much less than what you're actually going to see out of a Hunter's curve or a lot of the other methods or modified Hunter's curves for sizing up these mixing valves and figuring out your peak demand flow. Dan, you remember that webinar we did a while back with Pete Skinner and Gary Klein?
I do, yes.
Holy cow, that was just an eye-opener, wasn't it?
Yeah, I had talked to Pete when he was doing some of the measuring of actual flows in that facility, and it was pretty amazing how low actual flow really was. I think it was down around 9 gallons per minute.
Yeah, and to give you guys a little backstory into that, so we did a webinar a few years back. It was kind of like a case study. It was a really cool webinar. They had a nursing home facility, I believe is what it was, and it was already up and running, and they were going to be building literally an identical one right next to it. And in the existing building, they had, I believe it was 1.5-inch mains. And it was a very big system, and they decided to do the legwork. They decided to figure out exactly what that build, because they're building an identical one right next to it. Like, what better time do you have for a little bit of research, And so what they did is they put ultrasonic flow meters on that particular system that was already in existence and already operational with 1.5-inch distribution. And over the period of, I don't even know how many weeks, the highest demand that they ever saw from that building was, I think it was a little less than 10 gallons per minute. Okay, right. Now that is just wild. The fact that you've got 10 gallons per minute going down an 1.5-inch pipe, they could have downsized that to 1-inch pipe, or they might have even gotten away with 3/4-inch pipe, depending on where it looked at on the system there. But the fact is that you've got a lot of room there to save quite a bit of money and really help with system design. So definitely check these out as far as different ways. Don't just pick one way. The fact that calculator is completely free, you can throw some numbers in it, and 2 minutes later you can get an idea of what's going on. Might be a little bit of help for you guys for sure.
I think there's a lot of states and municipalities that are starting to adapt the IAPMO water demand calculator as a tool to be able to calculate design flow rates as well.
You're right, Dan. They actually allow the water demand calculator right now in the state of Wisconsin where I'm sitting. So
Yep.
so if you are in the state of Wisconsin, definitely use that to your advantage. Like I said, I've done it before in several different methods to where you can get wildly varying design flow rates based on
Right.
hunters or modified hunters or this water demand calculator. So definitely check that out. So once you do have your peak demand flow, obviously then you can go back to that eye chart that I showed you before from our literature. The fact that you can go in there and you can pick out a valve with confidence. You can make sure that it's the right size valve for what you need. And sizing these valves is not just a bigger is better kind of thing. And it's not a thing that you want to tempt fate with on that one. But the fact that you're going to pick the correct valve for the size and flow rate that you need and the pressure drop that you find acceptable. So definitely check that out. And when you get done with that, then obviously you've got to look into piping these systems. So you've calculated peak demand, you figured out the size of the valve you need, and it's time to get it piped up. And we actually, this is a diagram directly from our valve, our electronic mixing valve, but you'll see similar diagrams to these guys. And really, in all reality, there's two different ways here that you can kind of go about this on our particular diagram. You've got an option here for piping it up to a storage tank without a recirc tank tapping. And then you've got a more of a commercial size system where you do have a recirc tank tapping here. And what you'll see here is just some subtle differences. The fact that when the recirc comes back, it's going to hit this cold line. And what's going to happen with the recirc, especially during times of no demand, is the recirc is either going to go to the cold inlet here, as you follow my cursor, or it's going to backtrack around and go into the domestic hot water source and then back to the hot inlet of the mixing valve. Now, it's really important when you're piping this recirc system that you give the ability of the recirc to choose, or not necessarily choose itself, but the ability to go the direction it needs to go, either to the cold inlet or through the domestic hot water source, because you need to have the ability to be able to control the temperature, and the ability to control the temperature is based on whether or not it's going to go to the cold inlet or back through the domestic hot water source to pick up a little heat to bring that loop back up in temperature. Now, the subtle differences here being to this next one is that you're going to actually bring back the recirc. As you follow my cursor, you're going to split the recirc, and one side's going to go to the cold inlet, and just upstream you're going to have a check valve, so that this guy right here is going to go straight into the cold inlet, and it can't go anywhere else. Okay. The next one is going to go out to your tank tapping for your domestic hot water recirc, and so basically, in essence, you're splitting them up. And the fact is that you've got two kind of big advantages there. The fact that you're not producing, or you're not running into scenarios with reverse flow through any of your piping. And this might not seem like a lot of piping, but this could be a lot of piping depending on how it ended up on the wall. Okay, but then the other thing too is if with your tank tapping for your recirc somewhere in the middle here, it's usually going to have a better function with maintaining stratification within your tanks and everything like that too. So the other thing that you should notice, and with this particular diagram down below, is that you'll notice on a lot of thermostatic mixing valves that are out there, including our own, as far as the diagrams are concerned, usually you'll find throttling valves on these two lines here. Dan, what are you using those throttling valves for? They're very important, but they're definitely something that gets overlooked.
Yeah, typically it's used to create restriction so that the water can follow the path of least restriction, and at that point would be through your mixing valve to prevent temperature creep with a thermostatic. But with the electronic mixing valve being a ball valve design, you wouldn't need that.
Correct. So with thermostatic mixing valves, per ASSE 1017, you're not really required to have the ability to completely shut off hot or completely shut off cold. And that's kind of a problem sometimes, especially when you're doing domestic hot water recirc during times of no demand. If there's no demand from the fixtures, your recirc is coming back at 110 or 115 or whatever it's coming back at. And so the mixing valve is dealing with that, as well as whatever temperatures in the tank, which is typically 140 or more. And so when you're coming back at 110 or 115 and you need to distribute back out at 120, you don't need a lot of hot water in order to bring that guy back up in temperature. And so what happens is if the mixing valve, again, a thermostatic more importantly, doesn't have the ability to close down this hot inlet enough, you could actually be adding more heat to the loop than what the loop is giving off. And so by putting a throttling valve, especially on this line right down here, by putting a throttling valve down there, you're basically bypassing the ability for the mixing valve to control during times of no demand. You're restricting it so because it can't shut down that hot inlet enough. And as Dan mentioned, the fact that we've got a 3-way ball valve with our Legio mix, it does have the ability to do bubble tight close off on the hot and prevent recirc creep altogether. So it's a really big advantage here, especially with electronic mixing valves that are using a 3-way ball valve that's like our Legio mix, that you can prevent recirc creep during those times of no demand. So that way you're not bringing the whole loop up to whatever temperature is in the tank and then potentially scalding somebody that turns on that first faucet in the morning after a long period of inactivity. All righty. Now, this is just an interesting, very simplified diagram to kind of just go over the fact that the devil's in the details, okay? When we talk about that piping diagram before, translating it from a diagram over to the wall or to an actual job and everything like that, you put one check valve in the wrong place and it's going to lead to a lot of issues that were unforeseen. Now, check valves are very common in these systems, especially at the mixing valve. Typically, you'll have a check valve at the hot and cold inlet. It's going to prevent migration across the mixing valve, heat migration. It's also going to prevent cross connections, which are not typically common at a point of distribution mixing valve, but it's something that in a lot of places will require, okay? But in this particular case, again, very simplified diagram, the recirc comes back, and you'll notice this purple line here coming back, and it hits the cold inlet of the mixing valve. And so what happens here is the recirc comes back and it basically has only one way to go, okay? It's gonna hit that cold inlet and it's only gonna be able to go to the cold side because there's a swing check right here, okay? This swing check is going to make sure that literally nothing gets past it, okay? This was a job that was actually at a county jail, not too far away from where I'm sitting right now. And the problem with this is now the recirc doesn't have the ability to make it back to the domestic hot water source when there's no demand from the fixtures to bring the heat back up in the loop. So what they actually ran into here was a scenario of droop as opposed to creep. So as the time went on during times of no demand, it just kept losing temperature and losing temperature and losing temperature. And so ultimately, what ended up happening was the fix here was to basically gut that swing check. So they took the internals out of that swing check, and that was one way to fix the problem. And it did fix the problem, which is great, because then what it allowed to do, that recirc allowed to be able to go back through the cold side and into your domestic hot water source, and then back up through the hot to get to that hot inlet of the mixing valve. So now the mixing valve has the ability to determine which way the recirc flow goes, whether it goes to the cold inlet or back through the water heater to the hot inlet to bring the temperature up. And that's what's determining what direction this stuff is flowing, is the mixing valve. And so you need to make sure that you can get the BTUs you need to maintain the loop, but not too much and not too little. It's kind of like that perfect scenario. Mm-hmm. Now, a better idea, instead of just gutting that swing check, again, hindsight's always 20/20. A better idea would have probably been like what we showed before, where you actually have a parallel line coming off this circulator with another check valve, and then you would have actually brought it right into the tank tapping right here. So you could have left this swing check in place, okay, that was here. You could have paralleled off and hit this tank tapping, and you would have prevented any reverse flow and all that other fun stuff, and any potential for stirring up the bottom of the tank and ruining any stratification you've got into the tank. It's definitely something you should consider. But again, hindsight's always 20/20, and the system's up and running now, and everybody's happy. But I'll always think about those better ways that maybe it could have been done a little bit differently, for sure. All righty. Now, Dan and I were talking about this. We talked about some interesting piping scenarios, and we were talking about sizing of mixing valves and sizing of plumbing systems and everything like that. I just wanted to get out a thought that I had about sizing of plumbing systems. And Dan, you can probably attest to this just as well as I can, right? The fact is that we at Caleffi, we get calls a lot from engineers regarding hydronics and plumbing systems. And especially in hydronic systems, it's pretty common that we'll get calls from engineers regarding these systems and sizing of components. Like this guy right here on the left, this is a hydraulic separator, might be an air separator too, it doesn't matter what it is. But we'll get a call about that. And then the reason why they're calling is they're typically looking for our blessing to size down this particular device. Okay, they want to try to squeeze every last little bit out of whatever smallest one they can get their hands on. Okay, because obviously there's some value there. Okay, now on the other hand, we're running into plumbing system side of things, where again you've got a widely varying flow rates, but what we usually run into is that these plumbing systems are ranging anywhere from slightly to wildly oversized. Okay, you know, we talked about how to size these systems and figure out peak demand flow. It's no secret that smaller parts are going to be less expensive, okay? And that's why the engineer called about going down in a size about, you know, with a hydraulic separator or an air separator. It's you know, it doesn't hurt to ask is what it boils down to. But what I want to get across with this particular thought is, with more consideration to our sizing of our plumbing systems and things like that, between the smaller materials, reduced labor, lower distribution heat losses, smaller recirculation systems, there is an absolute ton to gain. I'm sure you're probably on the same wavelength as me, Dan, right?
Yeah, you're going to gain a lot of performance benefits out of sizing it properly versus just putting it in oversized. I mean, that valve's going to perform, it's going to be more stable in temperature control. You're going to have lower minimum flow rates to consider. So real importance in focusing on design flow rates and sizing properly.
For sure, for sure. And you know, I'm going to jump right in and play devil's advocate here. I'm ranting about how things are wildly oversized in plumbing systems, just due to how the means of sizing these systems that are available currently. You know, now I'm going to talk about systems where you're actually going to use multiple valves. So this is pretty hilarious. The fact that you know, we don't want them oversized, but there are situations where you might need to use multiple valves. So this is a different type of piping scenario, and this was actually in our pre-submitted questions for the webinar. This actually came from Michael from Pace Supply, one of our distributors out in California. So thank you, Michael, for that particular question that you popped in here. There's a good chance that your application might need multiple valves, and there's different reasons behind this. Maybe you just need multiple valves to meet the demand from the system. There's also a good chance that you'll need multiple valves for handling redundancy. Okay, the fact that, you know, if you need, you know, multiple and one goes down for maintenance or whatever the case may be, you have the system still up and running without interrupting service to the entire building. But what I wanted to get across here as far as piping is concerned is the ability to pipe these systems to where they're going to function properly. And I think the best way to go about this is through the use of reverse return, or if you might want to call it first in, last out, whatever you call it. The fact is that by doing reverse return or first in, last out, it's guaranteeing equal flow through all of these valves. I've seen it plenty of times where equal distance piping and a bag full of good intentions just don't cut it. And it's something that by doing this reverse return, it's a very simple way to make sure that, you know, you don't have to worry about equal distance piping and everything too. What do you think, Dan?
I agree with that. I definitely agree with that.
Yeah, and Michael also asked about electronics and controls. So obviously with an electronic mixing valve, you're going to have a control for the valve. Do you need to have one, Dan, for every single valve, or can you actually use one control for, well, all three here?
No, you do need a control for every valve, and that's important. The mixed outlet sensor is located right at the outlet of the valve, and that's what communicates back to the control to control the actuator. So it's important that each valve have its own control. It's also important, like Cody mentioned, and you know, for redundancy or service, if you need to get in and do some service on one of the valves, you can shut one of the valves down completely. Let's say, you know, the maintenance mechanic is in the boiler room or control room, and he drops a ladder or a hammer or something, he knocks an actuator off the valve. You know, you can shut that valve down while you order a new actuator, and the system, you don't have to take the system down. You can still run off of the additional two valves. So it's important to have a control for every unit.
Yep, and you know, like you said, the fact that if somebody knocks an actuator off by accident, it happens. He drops a ladder or whatever. The fact that you can still keep everything up and running and no harm, no foul. Redundancy is definitely a good thing there. So yeah, you know, whether it be, you know, you're designing around peak demand or you want the redundancy or both, that's a fantastic way to go about things here. All right, so now we're going to move into the thing that every guy who works with pipes is loving, and that's wiring and setup of controls. This is one of the things that really pushes a lot of engineers away. And what we wanted to get across here is that it's not nearly as bad as what you can imagine as far as wiring and programming these things. It's really actually quite simple. So all electronic mixing valves will require some wiring and setup. Dan, you want to go through this one here?
I think this is probably the most intimidating part for a plumbing contractor, you know, is now they have to deal with electric. So when you look at it, it's very easy. I mean, you have an actuator with three wire control that has to tie into the unit. You have two wire sensors, and then a 24-volt power source coming in. So it's very easy to connect up and wire. One question we get is, you know, how close does the control need to be? It doesn't need to be right near the valve. You can extend it up to 800 feet away. Once it's wired, it's simple from there. Just 3 questions. You set your date, your time, your location, and it's off. And ours is factory set for 113 on a mixed outlet once it's commissioned, and the valve is maintaining at 113. You do have the ability to tie into a building control system, which we'll talk a little bit about. You can add a gateway to connect to it with BACnet or Modbus directly into the control.
Yeah, and you know, a lot of times this control scenario here with the gateway to get it over to your building management system, that's typically handled by your controls engineers or your controls guys anyway on the job site. But it's very common to where you're going to want to connect these up to building management systems, and we'll talk about some of the benefits of that later. But the fact is that you could, even in the scenario of that last diagram where we had 3 valves on the system, you can actually connect multiple valves up to a single gateway. I think you can get up to roughly about a dozen of them on there. Right. So if you are doing, you know, the ability to connect to building management systems is something that we're seeing a huge demand for, the connected type systems in a lot of these larger commercial buildings. So again, like Dan mentioned, 800 feet away, the fact that you can actually put it in a building engineer's office or somewhere outside of the mechanical room to where maybe somebody could keep a better eye on it or whatever, if it's something that they want a little bit more, you know, personal time with, kind of thing, to make sure that it's doing exactly what it could. You can put it anywhere up to 800 feet, which is pretty impressive. So so definitely consider that. Now, if you are really trying to avoid wiring altogether, there is another option, and this is pretty common amongst thermostatic mixing valves as well as electronic mixing valves, the fact that you can actually get it in a racked assembly like this. From my experience, engineers and contractors love racked assemblies because it just really lessens any chance for errors in translation when it comes from the drawing to the building. And anytime you can reduce the potential for errors and increase productivity on the job site, that is a win-win for everybody. But what you've got with these racked assemblies is you've got check valves in all the right places, isolation valves in all the right places. But my favorite part by and large is the fact that with our stations, everything is pre-wired. Okay, and Dan, you're laughing, okay,
Yep.
because obviously this is a point of controversy with a lot of contractors and engineers, is they don't want to bring another trade into the mix. They don't want to bring the electricians in there. They want the plumbers just to be able to do their thing. And so that's what we've got here with this guy. The fact that you've got the sensors pre-wired from the factory, you got the actuator pre-wired from the factory. You don't see it in the picture here, but there's actually a 20-foot cord with a plug-in transformer. The reason why you don't see it is because the marketing department didn't think it was the prettiest thing in the picture, so it got deleted. But with that in mind, you got a 20-foot cord. So literally at that point, you've got a contractor hanging an assembly like this. So, you know, you see it all the time. It doesn't matter if it's skidded out boiler packages, a skid of you know, a racked assembly for pressure booster pumps and things like that. Anytime you can get this stuff and do this, and it's just going to make the job go so much easier. Okay, so they get this assembly here. It's going to show up literally looking right like this on the screen. They hang it on the wall. They make their 5 piping connections, plug it in, and then as Dan mentioned before, you've got those 3 questions. It's going to ask you date, time, and location, and from there, it's going to be a mixing valve at 113 degrees. Really simple.
Yeah, like Cody said, all your check valves are in the right place, so it just takes that, boost the level of confidence for the customer, I guess, that everything is going to be set up and operational with just a plug-in of a transformer and 5 connections.
Yeah, super, super easy. Okay, so we've gone through kind of some of the planning stuff as far as, you know, sizing. We've gone through piping. We've gone through some of the electrical stuff, some of the things that you might be running into when transitioning from thermostatic to electronic. Now we're going to talk about some of the functions of an electronic mixing valve, and obviously, I think one of the big things here is that you got to remember that these mixing valves are all basically tested to the same standard. So what we're talking about here is ASSE 1017. They're all tested to the same standard as far as their accuracy of temperature based on a flow rate and everything like that. So they're all going to be going to that same standard. So they're all going to be pretty close as far as accuracy, as long as they're applied appropriately. But one of the things that you probably might be looking into going forward into the future is the ability to do thermal disinfections. This is something that is a very common application around the world. It's definitely something you're going to probably miss out on if you're doing thermostatic, but it's the practice of using high temperature water to manage Legionella in your domestic hot water distribution. And when I say manage Legionella, you know, and any bacteria in your domestic hot water distribution, you're just managing it. You can never completely 100% eradicate all the Legionella in your system, because as you bring more fresh water in from outside, you're going to bring in more Legionella, but the intent there is to make sure you're keeping those levels as low as possible to limit the risk of Legionella in your system, because obviously as Legionella gets into your lungs and things like that, you're going to be not having a good time, is what it boils down to. It's similar symptoms to pneumonia. It's a 1 in 10 mortality rate. It's something that you want to avoid. So Dan, you want to go over how that thermal disinfection stuff works and what that control can do for you?
Yeah, so what we're doing when we program thermal disinfection is you're setting up a schedule for the building, and you can set up what days you want the thermal disinfection to occur. And at that point, what it's going to do is it's going to elevate the source water temperature going through the piping using the recirc pump to keep that water moving for a period of time to control that Legionella bacteria. You know, if we look at the chart on the right, at different temperatures, you can kill the Legionella bacteria within a certain time period. So like, for example, at 151 degrees, it'll die within 2 minutes. So with our control, what that'll do is it'll elevate the water temperature. We're factory set to 140, and it'll run until it sees the recirc temperature coming back at 135 for 30 minutes. And at that point, it's determined that the bacteria has been killed or controlled.
Yeah, and that is a point in time. You know, you're managing and killing off that bacteria in a point in time. But the idea is that typically what they do throughout other markets around the world is they'll do that thermal disinfection typically once a day. You know, every night at, say, like 2 or 3 in the morning. Typically you're doing it at periods of no demand or little demand. But obviously sending out 150 degree water through your distribution system can have make people a little nervous, whether it be designers or contractors or building owners and stuff like that. So there's some things that you got to be kind of mindful of. One of which is, if you are doing thermal disinfection, you need to make sure you have anti-scald protection everywhere. Anywhere an occupant of the building can touch hot water during that stage or that thermal disinfection phase, you need to have anti-scald. You need it, whether it be a point of use mixing valve like one of these little guys underneath the sink, or a fixture with anti-scald protection built right into it, thermostatic anti-scald protection. You're definitely gonna wanna do that. You need to circulate as much of the system as possible, which is something that we're already doing. We'll talk about that a little bit more too later. But the other big one is that you need to make sure that your materials in the system can handle those higher temperatures that you're going to be running through there. Now, obviously copper is not that big of a deal, but you get into some of the products like PEX, and one thing to kind of remember is that PEX, as your temperature goes up, your pressure rating goes down. Yeah. And so, you know, you want to make sure that you know, you're not exceeding any of that stuff. I've also seen it where some plumbing stops are only rated to 140, so you got to be careful with that stuff. But in the end, by doing thermal disinfection, you have the ability to manage Legionella bacteria with stuff you already have on the job. You've got a mixing valve, you've got a domestic hot water source, and you can do that very simply. And what's really cool with an electronic mixing valve that has this ability, like our Legiomix, is that can be fully automated. This is not something that requires manual intervention. You can literally set it up as a schedule within the control to make sure that it's every night of the week at 3 o'clock in the morning. everything goes easy as pie, okay? And so with that in mind, you've got the ability to manage Legionella without adding any extra equipment, whether it be chemical injection or anything like that. You're not spending any more money on extra equipment, whether it be upfront cost for equipment or maintenance costs, service costs, chemical refills. For the life of the building, you've got something that's going to be a much safer option and much more cost to benefit ratio option that's going to be a lot better for your building owners. So when it comes to programming, Dan, you want to walk through this guy here real quick? If as far as setting it up and making sure you've got all your settings correct if you are doing thermal disinfection here.
Yeah, so programming it is pretty easy. Like we mentioned, it comes factory set at the 113. So you would, jump in at that first arrow, the set 1, and that's where you adjust your outlet temperature. That's what it's going to mix to. Set 2 is going to be the temperature it's going to elevate to for thermal disinfection. So we mentioned that, the higher the temperature, the quicker it kills off that Legionella bacteria. It comes factory set for 140. You can change it from there. When we look at next on set 3, that's what the recirc return temperature sensor is looking for the temperature to come back at. And that, what it's doing is it's using that to confirm that the thermal disinfection cycle is complete. And our control, again, would let you know if it doesn't see that cycle be completed within the set amount of time. Next one is program days. That allows you to set up what day of the week it's going to do thermal disinfection. You can set it up to, typically we would recommend it once a day, but you can confirm what days of the week that will happen.
Yeah, and we actually have, there's one application that we saw, it was a school out in the New England area where they were just doing thermal disinfection once a week. I think they did it on Saturdays, if I remember correctly. The idea that they would, make sure everybody's out of the building and all that fun stuff, so.
Right. Yeah, and then you can adjust the time on, that's what time it'll start thermal disinfection. Factory set for 2 a.m. and then time off would be the end of your disinfection cycle, which is set for 3 a.m. Temperature weight, or the T weight, is how long it's going to take for that recirc loop to get up to temperature. So you may initiate thermal disinfection at 2 a.m., but it may take 2 minutes to get that loop up to 140 degrees to start that disinfection cycle. And then the last one is T-min. That's going to measure the mixed outlet temperature on the mixed outlet temperature sensor to confirm that thermal disinfection has been completed.
Yep, and so we kind of glossed over it a little bit. I noticed in the comments here, in the questions pane here, so thank you very much for pointing that out. The idea of thermal disinfection, again, it's the idea that you can use high temperature water to kill bacteria, okay? So you don't have to use chemicals, you don't have to use any particular equipment. You're just literally using high temperature water, and it's proven, it's known that by elevating the temperature of the water, you have the ability to kill off Legionella bacteria. And
it's really
as
temperature and time.
And time, you're correct, yeah. So as if it's much higher temperature, the time decreases quite drastically. Like 160 degrees, you can instantly kill it, versus 140, it's going to take a little while longer. So, the fact that if you are looking into these types of applications, this is something that, again, with an electronic mixing valve, you can do in a fully automated fashion. Now, I have seen scenarios where they use thermostatic mixing valves, and they'll actually create a bypass around from hot inlet of the mixing valve over to mixed outlet, and they'll actually pipe it in with a valve to basically do a thermal disinfection, like a manual intervention kind of thermal disinfection. They'll actually use that valve to open it and allow it to bypass the mixing valve and send out that high temperature water directly from your domestic hot water source. Now, the issue there is that it requires a lot of manual input, obviously. You could potentially automate that, but you're looking at some kind of PLC control or whatever the case may be. What's awesome with electronic mixing like our LegioMix is that we actually have the ability to do this fully automated. Not only that, but we also have the ability to confirm successful or failed disinfection, which I think is absolutely crucial, because doing it is one thing, but having the data there to back you up is another thing. And how we have the data there to do that is we have a data logging function literally built right into the control, okay? It will log all those successful thermal disinfections, or if it failed, it'll log that too. And it also does average hourly temperatures for the mixed outlet sensor and the return temperature sensor that we talked about before. And so that is absolutely awesome to have that data available to make sure that it's doing exactly what you want it to do, and cover your rear end, so to speak, for any liability issues that might come about as well. All right, now, normally, you're going to be setting up your domestic hot water storage to 140. That's most code requirements is going to be 140 degrees Fahrenheit, okay? But if you are doing thermal disinfection, there's a good chance you're going to want to raise that storage temperature up to 150 or 160 in order to do that. So how do you go about doing that to make sure that you can raise that storage temperature up so you can complete that thermal disinfection? Do you have to have the storage at 160 all the time in order to make sure that you can do thermal disinfection at 2 in the morning every day, or do you raise it up? Can you raise it up? And in this particular case with our Legio mix, we actually do have the ability to allow you to work with mechanicals in order to raise the temperature of the storage tank. So you don't have to keep it at a high level all the time. You can keep it at 140 all the time, and then during disinfection, raise that storage temp up. And that's through the use of dry contact relays that are on the back of our controls. And the one we wanted to talk about here real quick, because a lot of people have questions about this, and this is something that comes up quite frequently, is how on earth do I make this work and interact with all the controls? And it's through those dry contact relays, relay 3, terminals 5 and 6 here, that during thermal disinfection, that dry contact relay closes. And if you're using your building management system to basically figure out the set points for your domestic hot water storage, you can use that relay 3 as a, if relay 3 closes, then the domestic hot water storage set point will go to 160 or whatever you want it set to. It's pretty straightforward there. But if you are doing full mechanical, and this is quite a lot going on here, but if you're doing full mechanical, there's an easy way to go about doing that too, okay? And like I said, it looks like it's going along, a lot going on right here, but it's really not too bad. Normally with your boilers and your domestic hot water storage, you're gonna have a boiler and you're gonna have an aquastat in the tank that's going to come back to the boiler, tell the boiler to turn on when the tank gets too low and off when it gets to the right temperature. Gonna turn on the boiler as well as the circulator. And what you're gonna wire in parallel with that normal tank thermostat or that aquastat is a second aquastat that's gonna be set higher to your normal disinfection temperatures. And then this second aquastat is actually gonna be wired in series with relay 3. So obviously this aquastat is gonna be calling all the time. It's gonna be closed and wanna tell the boiler to turn on to raise it to the temperature that it's set for, but it's gonna be stopped here in series with relay 3. So it's only gonna happen during thermal disinfection cycles that you have programmed into the control, like Dan talked about before. Really straightforward. You know, it's not too hard. You just got to add that second aquastat, wired in series, and you're off and running again. Okay, so we've gone through some of the things as far as programming and control, setting up thermal disinfection, why you're doing thermal disinfection, and what we want to talk about here is balancing. Okay. Balancing is the next part of the equation when it comes to making sure that you have the ability to do thermal disinfection, because balancing has always been, and always probably will be, something that causes a lot of headaches for engineers, contractors, building owners, and everything like that. But when you're adding thermal disinfection into the equation, balancing becomes that much more important. Okay, making sure that you can get hot water to the, to these recirc valves and to these branches or these risers. Because if you can't guarantee it during normal operation, during thermal disinfection, if you can't guarantee that high temperature water is going to get there to make sure that you can kill off that bacteria, that's something that you need to be worried about. You need to be able to guarantee that those branches came all the way up to temperature like they're supposed to and kill off that bacteria exactly the way you want it to. And again, it still applies to just regular balancing too, which a lot of times can look like a mixing valve issue and things like that we want to avoid. Okay. So just talking about balancing valves here, want to talk about a couple of the different types here, and typical balancing valves, like what we see on the left-hand side here. This is a static manual balancing valve here. They take a lot of time to get set up properly. And when I say set up properly, that's with your fingers crossed and you're hoping, please, 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 they all get set up properly. Dan, do these always get set up properly?
Oh, no, not exactly.
Not exactly.
It's definitely going to require possibly may require another contractor to come in as well.
Correct. So, yeah, you might have a tested balance contractor come in. It's usually right at the end of the job, and everybody's itching to get occupancy, and they want to make sure that this gets done right. So everybody's, you know, on the contractor's back to get this thing balanced. If I had a nickel though for every time a contractor told me that they set all these manual balancing valves to about halfway and they keep their fingers crossed and, you know, whatever else, I could probably retire already. But with that in mind, we want to talk about the fact that if there's anything that can be done to ensure that this balancing process is easier or even not required, it's something that you definitely need to consider, okay? And what we've got here on the, and as a company, we've got several balancing valves that are fully automatic or fully dynamic and automatic, to where you're literally not having that whole balancing conversation at all. It's literally just putting the valve in the pipe and walking away in some cases, okay? And what we've got here with this picture on the right-hand side is a set of thermal balancing valves. So instead of, you know, basically setting a specific flow rate, with these thermal balancing valves, you're actually going to be setting a specific temperature. Okay, you got a knob on here, and on the inside of this cartridge, you're going to have a thermostatic cartridge, a lot like a thermostatic mixing valve, and you set this knob to whatever temperature you want. So after your last fixture, you know, you start bringing that recirc back to the express riser, or the riser, or the branch going back to your recirc, your common recirc. You're going to set this guy to whatever you want that last fixture to be at. So if you want it to be 110, you're distributing at 120. You want this guy to be 110. You set this knob to 110. And at that point, that thermostatic cartridge inside the valve will modulate to maintain that temperature. If it's below 110, it's going to open up a little bit more. If it's at or above 110, it's going to start closing down. It never closes off completely, because it's always letting a little trickle through there to make sure it can kind of figure out what's going on inside that system. But really, this is the ultimate in hands-off recirculation balancing, okay? Now, if you are doing thermal disinfection, we've been talking about thermal disinfection a lot, and high temperature water. Obviously, if you've got a balancing cartridge in here that's set to 110 degrees, if you're going to start jamming 150 degrees down the pipe, this guy's going to want to close off as much as possible. So what we've actually got here is the ability in this second cartridge bay here to do a bypass. So if you are doing thermal disinfection, you can have a bypass to where if the temperature goes up, you open this bypass so that way you can increase your flow rate and complete that thermal disinfection as quickly as possible. We've got a couple of options there, whether it be a thermal bypass or an actuator control bypass like what you see there in the picture. But really, in all reality, it's pretty straightforward if you're doing it. But this, again, the fact that you can actually have a balancing valve that does not really require much for input besides twisting the knob at the top, which is a lockable knob, so you can prevent a lot of the maintenance guys from messing with it afterwards, kind of thing. But you basically set that knob and you walk away and you're done, okay? This is something that, again, anybody needs to consider, because it's going to be so much more important as time goes on, especially if you are doing thermal disinfection, to make sure that you can get that hot water everywhere it needs to be, and obviously save on wasted water as well.
Yeah, I think with the focus today on energy efficiency as well, you always want to have the thermal balancing valves paired with a variable speed pump. So from the standpoint of energy savings, that variable speed pump will ramp up or down as it needs to based on the balancing demand of the building. You'll guarantee every circuit gets balanced properly and you conserve energy. So I think that's
For sure, yeah. I mean, the fact that these thermal balancing valves are modulating, that's going to pair perfectly with a variable speed circ that's running either a constant or proportional pressure mode. The fact that circulator will ramp up and down with the modulating valves. The one thing I will say is that there's a number of domestic hot water like recirc pumps out there that will have a variable speed function that's based on temperature. So it'll actually have a sensor back on the line, and it'll modulate the flow in from the circulator based on that temperature. If you are using thermal balancing valves, I would not do that. You need to make sure it's either in a proportional pressure or constant pressure mode, because by using that sensor to ramp it up and down, you're basically got two things trying to control the temperature. One is the sensor and the pump, and the other one being the thermal balancing valves. You need to make sure that they're working in harmony as opposed to kind of conflicting with one another. So definitely keep an eye on that.
Right.
All right. Now, the next one we want to talk about is dead ends and runouts and things like that. that you might be running into a situation where maybe you're preparing for a future expansion. But when it comes to Legionella and bacterial growth, this area down here in the yellowish orange circle here, that's going to be a complete dead end. That is an area where there will be no flow through that pipe, and that is a scenario that should literally never happen. If there's no flow going through that pipe should not be there, because what you're basically creating when it comes to bacterial growth is a petri dish, okay? And that's something that you really want to avoid, okay? And it's also a great thing to mention, this was brought up in the pre-submitted questions as well, is that, you know, warm water is obviously a good place for bacteria to grow, but cold water can become warm water. And so dead ends on cold water should also be kept out of the loop as well, or kept out of that scenario. So make sure that you're getting out of those dead ends. You know, cut into the pipe later if you need to add on, to expand, and do whatever you need to do. But those longer dead ends, definitely something that you want to avoid. And on the other end of the spectrum, you're going to have runouts. The fact that you've got from your riser a section of pipe that's going to go to your fixtures that is going to have the potential to sit stagnant during the times that you're waiting for the fixture to open. These runouts obviously need to be kept to a minimum for a couple reasons. One, you know, this runout here is not going to have any flow through it from the domestic hot water recirc. So whatever you turn on this fixture, you're going to be waiting for hot water from the riser. So by keeping this runout to a minimum, it's going to, again, reduce that wasted water and everything like that. But it's also going to reduce the amount of water that has the potential to sit stagnant and basically grow bacteria in it, waiting for these fixtures to open, okay? So limit the amount of runouts on these guys, eliminate dead ends for sure. And again, that's going to help you a lot with your bacterial growth and in your systems there. And this doesn't matter if it's electronic or thermostatic mixing valves, but it's something that we wanted to put in here to make sure that we're really stressing the fact that we want to have a clean system to make sure that you're doing the best you can.
Right.
Okay, now want to talk about troubleshooting. This is one of those ones. This is a topic that could have gone into the planning stage. But Dan, do we normally talk about minimum flow requirements in the planning stage, or is it after everything's installed?
It's usually after everything's installed and they're seeing a lot of temperature variations.
Correct.
And generally when that call comes in, it's when there's low or no flow in the building and they're seeing that valve. One thing you have to remember with the thermostatic valve, because that sensor's located right at the mixed outlet, so close to the mixed outlet, it reacts really fast and it's real-time temperatures. So, I mean, a thermostatic valve, you may have temperature changes, but you have no way to verify it. With the thermostatic, with electronic valve, you're going to see that on the controls, so it becomes very evident.
Yep. So what we're getting at here is every valve, and I brought up this little point of use mixing valve. Every valve under the sun, whether it's a little guy like this or a big 3-inch electronic mixing valve or a thermostatic of any type, is going to have a minimum flow requirement. Now, if you're not meeting minimum flow requirements, what's going to happen is that the hot and cold coming into the mixing valve, it's not going to be coming in fast enough to create the turbulence needed to get a good mixed temperature at the thermal actuator, or in the case of an electronic mixing valve, the sensor that's in there. If it can't get a good mixed temperature reading, maybe that sensor or actuator is reading all hot or all cold. And what's going to happen to that valve is it's going to hunt all over the place. And your average contractor is going to look at that and go, what in the world? And then what are they going to do with it, Dan?
They're going to want to take it out and change it.
Correct. Okay.
Yeah, and take it out and replace it.
Exactly. Okay. Because they're going to think, hey, this is a bad mixing valve, when in all reality, it's probably not the case. So with that in mind, making sure that you're meeting minimum flow requirements can be pretty difficult, especially when you got some of these larger valves. And one thing you can do to actually circumvent that, especially if you're coming from a high-low mixing valve, is by using constant recirculation. And I know some of you are scoffing at me, the idea that constant recirculation is not allowed because of energy code requirements and things like that. But the fact is by running continuous recirculation, you're going to use that circulator pump to meet the minimum flow requirements of your valve. And not only that, you're going to prevent stagnant water scenarios to help limit the amount of growth of bacteria in your systems. And I think it's just an entertaining thought, the fact that we go to such great lengths on the heating and air conditioning side, the air quality side of a building, for air changes and making sure you're getting constant fresh air, and the amount of energy that's consumed by doing that when in all reality, a little bitty recirc pump and some heat loss of your distribution is a big no-no for energy conservation. So I think that one day the idea of constant recirculation is going to be a requirement. But with that in mind, we're still at that point. So definitely make sure that you're meeting minimum flow requirements, either with constant recirculation or by the demand of the system. It's something that you definitely need to keep an eye on. All right, now we're coming down the home stretch here, talking about troubleshooting. Now, troubleshooting might not seem like such an awesome thing for some of the designers out there, but it's something that your building owners are definitely going to have to deal with, whether it be the minimum flow requirements or, in this case, cross connection. Dan, you want to talk about that hotel in Madison that we were talking to?
Yeah, we had a hotel locally that put in one of our electronic mixing valves, and the benefit of the data logging actually became really evident. I was on a tech call with the contractor. He was back on site because 3 days in a row they had a complaint of loss of hot water, and so he's back on site to try to determine what's going on. He's looking at the control. He calls me, so we jumped into the log and was able to verify that at 6 p.m. 3 nights in a row that the temperature dropped in the system. So that gave us the ability to go back and determine, okay, what's happening in the building at 6 p.m. 3 nights in a row. And what they determined is that's when the cleaning crew was in. So they started looking around and they were able to locate a cross connection at one of the mop sinks.
Very common, yep.
But had they not had that log to look at to understand exactly when it's occurring and what was occurring, one, they may have replaced the control in the mixing valve, or they wouldn't have possibly thought of looking for cross connection.
Correct. And in the world of cross connections from hot to cold in these buildings and everything like that, the mop sink is like the #1 on the most wanted list. And what usually happens with these guys here is you've got the hot and cold, they'll have a hose coming off just like what we see here, and then they'll have a valve on the hose somewhere. So that way they don't have to go back and adjust the temperature at the handles and stuff like that. But at that point, with it valved off at the end of the hose, you've got a direct cross connection between hot and cold, which can drag down your recirc temps and cause a lot of issues that might look like a mixing valve. But like Dan said, you dig into it a little bit deeper, that guy saved a lot of time in screwing around and replacing mixing valves that didn't need to be replaced by using that log data that we talked about before to really nail down exactly what was happening in those systems.
Well, it saved him a lot of troubleshooting time too, because he showed up on site and the valve was working fine. So now he's trying to diagnose a problem that's not occurring, and it's challenging. So this was able to at least point him in a direction and saved him a lot of time on site.
Coming from the field, one of the worst things you ever wanted to see on a service ticket is intermittent operation or intermittent failures.
I know.
That is one of the, you pull your hair out and everything else. But then the last thing we wanted to talk about between thermostatic and electronic mixing valves, and this is something that is a little bit more specific to our Legio mix, but the fact is that when you look at thermostatic mixing valves like this big guy on the left-hand side here, it's very common where these thermostatic mixing valves are going to need to be rebuilt once a year, sometimes even more, depending on how harsh the water conditions are. And one of the features that we have built into our Legio mix is the ability to do a function called anti-clog. And now, one thing that I want to point out first is that because we use a 3-way ball valve, we've got a big wide open passageways through that valve that are going to be less prone to catching a lot of debris. But then you couple that with our anti-clog function, and what that does is it does at 3 o'clock in the morning every day, it does full rotations of the ball inside the valve body multiple times in both directions, to where if there is any scale or debris on the ball, it's going to use the seals inside the valve body to wipe it clean. Okay, and in this particular application here, they were, like I mentioned before, rebuilding this mixing valve on the left-hand side once a year. Okay, these electronic mixing valves went in 2018. They have not touched them since. I confirmed this just a few weeks ago. It is a beautiful thing, because if you think about it, that's another cost that the building owner is going to have to incur, not only to pay the service guy to come out and rebuild the mixing valve, but the cost of inconvenience to bring down the entire building in this case. It's a huge thing. So looking at the cost of life over the life of the mixing valve or the life of the building is definitely something that needs to be considered, and handling harsh water conditions is something that an electronic mixing valve does have the ability to do, and in a lot of cases many times better than what you've got with thermostatic. Okay, so from there, we wanted to just do a quick review. We talked about planning, the things that if you are looking at switching over from thermostatic to electronic, don't hesitate to give us a call. We want to talk to you about these particular products. Make sure that you're comfortable with it, whether you're an engineer, designer, contractor, whatever. Make sure that it's piped properly. Using those pre-piped assemblies is a great idea. Setup and disinfection and things like that we talked about, the programming of the control is not nearly as intimidating as one might think. And then when it comes to troubleshooting and maintenance, the idea of having data to back up any diagnosis that you make through that data logging function on the controls is absolutely priceless. You're gonna see more and more electronic mixing valves coming down the pipeline. I know there's some particular hotel jobs that are flat out requiring electronic mixing valves going forward, and it's going to start becoming more and more prevalent. And so if you want to get ahead of the curve, don't hesitate to call us. We've got a great tech support team back in Milwaukee. Myself, Greg, Matt DeLuca, and Kevin Freet, we're all here to help you guys, so don't hesitate to give us a call. We want to stop and talk. I don't know if you caught any questions here, Dan, too, in the questions pane that you wanted to touch base on, or I don't know if Max is still there or not. I'm looking through here a little bit. One of the
Hey, Cody, Dan?
Yes. Yep. Hey, Mark.
Yeah, Max had to check out. There's a question that just came in from Ronald back on the mop sink. Will check valves on the hot and cold supplies at the mop sink stop cross flow like at the hotel you referenced?
For sure,
Yes.
and that's exactly what happened. Is you add check valves to that guy and everything is primo again. And that's why, you know, anytime you can have a cross connection outside of your mechanical room, like at a fixture, okay, that's something that obviously you want to avoid. And one of the more typical places you'll find cross connections is a mop sink. The other ones are going to be any type of single handle fixture. Okay, that's shower valves, that's single handle faucets at your kitchen sinks. There's a number of manufacturers that are pretty famous for having cross connections at cartridges. In a lot of cases, it's just replacing the cartridge and you're off and running again. But when you look at like little point of use mixing valves here, these are ripe for possibilities when it comes to cross connections from hot to cold. And per ASSE 1070, for example, this particular guy right here, it's required to have check valves at the hot and cold to prevent cross connections from one side to the other. And in my opinion, at a mop sink, it should also be required. Yeah. Another thought too is I've got one of those real nice touch faucets at my kitchen sink. We leave it on hot all the time and then just go up to it and touch it and everything like that. But if you leave it at a mixed temperature, that could also create a cross connection. And if you'll notice with those particular fixtures, mine in particular, it came with check valves specifically for the 3/8 connections at the plumbing stops. So that way you could leave it open and prevent that cross connection scenario.
Another question came in concerning the anti-scald point of use mixing valves during a time of disinfection. Relative to the temperature, the high temperature that you disinfect at, how resilient are anti-scald mixing valves to those high temperatures? Are they rated to handle them, or does it depend on the make?
Well, you know, I can really only speak to our models that we have available. I don't know the exact temperature. Mark, you might have it if you were doing the digging there, but like our little point of use mixing valves are definitely rated to over 200, if I remember correctly. So they should be able to handle it no problem without any issues for those types of applications where you are doing thermal disinfection.
Yeah, I think it's over some value over 200 for that.
I want to say it's 210 if I remember correctly, but.
Yeah, but that's a good point. I think Drew mentioned it, is that the higher the temperature you have and the closer the restriction is that the water goes through, the more chance you can have scale buildup, and thus that's the biggest Achilles heel for any type of thermostatic mixing valve is scale building up, which also brings up the point about the Max or Mr. mixing valve, the Legio mix, where you wipe it away before that scale has a chance to have any drag effect on the operating mechanism. So, but that was a good observation from Drew.
Yeah, for sure. Well, yeah, we appreciate your guys' input. I think we got to most of the questions. There was one here about flow meters and stuff like that to log data and stuff like that. We'd have to get back to you on that one. There's some ultrasonics out there and everything like that you can look into. I've heard of some places actually renting them as well, but we'll get back to you a little bit later on that one. Just go through the finishing slides here. If you like our webinars, definitely check out our podcast. Greg and Dan do a fantastic job talking about day-to-day stuff that we get regularly questioned about on our podcast. And especially as a contractor, you got that time going to jobs, definitely check that out. And then I actually do a little series called the 5 Things You Need to Know. It's a quick little series for those with attention spans that aren't just ready for the Coffee with Caleffis yet. These guys are going to be about 5 to 8 minutes. You can bang right through them really quick. We talk about Legionella. We talk about different types of hydraulic separation, all that fun stuff. And then definitely check us out on social media. We're on all of the majors, YouTube. We've got tons of content there. This webinar will be on YouTube probably next week, and all the different socials out there. And engage with us. We'd love to see your installations. We'd love to interact with you guys there. And if there are any questions, don't hesitate to reach out. And again, thank you so much for your time. And thanks, Dan, and thanks, Mark and Max too. So,
Yes.
all right, guys, have a great day.